kids. It's Mr. Yo, your science bro. And today I just want to talk your physics reference tables and see what we have done on this. Well, if we take a look at this first page, we see we have done all of this. Every single thing here. We know the value of big G in the universal gravitational constant. Remember, G equals m1, m2 over d squared. Acceleration due to gravity, speed of light in a vacuum, speed of sound at standard temperature and pressure is about 331 meters per second. We have the mass of the Earth and the Moon, radius of the Earth and the Moon. That's how we would find gravity using it in that universal gravity formula. Again, more universal gravity formula. The electrostatic constant in electricity, the elementary charge, a coulomb, an electron volt, Planck's constant. We get down to these last four things, a universal mass unit, and then the rest mass of the electron, proton, and neutron. We have not covered this yet. Prefixes of powers of 10, yeah, we got that. Approximate coefficients of friction, got that. Kinetic and static, we know what that means. Electromagnetic spectrum, we have now covered that. The absolute indices of refraction, your N values, have that. Remembering diamond is the most, right? That's why they sparkle. Right, so energy level diagrams. We determine the difference in the energy between any of these levels, and that will show us the photon, the nature of the photon that would come out to either cause the electron to jump up or the photon be given off when the electron jumps down from any of these energy levels. In the last episode, we showed the classification of matter, the particles of the Standard Model. Left that with a big question. How come there's 12 and we only use 3? We've gone through electricity, all the stuff on electricity. We've been there, done that. The circuit symbols, resistivities, right? R equals rho L over A. Right? We've done the resistivities. We've gotten waves, been all through waves. We're on modern physics now. We've covered this formula. This formula, the energy of the photon is energy initial minus energy final. Well, that has everything to do with this, energy initial minus energy final, the difference in the energies there. So we got this. So we are now down to the last formula in the reference tables. E equals mc squared. Okay, you can see what an easy formula it is, but you also know what a world-shaking formula it is. And notice there's nothing else that we haven't done. So we've gone all the way through physics, except for this last little bit. E equals mc squared. So we're going to want to take a look at this formula. E equals mc squared. Well, the energy is going to be measured in joules. Mass is going to be measured in kilograms. And C, the speed of light, measured in meters per second. Okay, so let's remember and make sure the units all work out. Remember, force equals mass times acceleration. 1 Newton is mass times acceleration. That's the unit of force that we use. All right? And if we break this down into the fundamental units, kilogram meters per second squared. Kilogram for mass, acceleration is meters per second squared. Right? Been there, done that. If we take 1 Newton of force pushing for 1 meter, that's going to be the work or energy, force times the distance. So the W is work or energy in joules. 1 joule is force times distance. Force measured in newtons, distance measured in meters. The joule is energy. And look at how it comes out. Kilogram meters per second squared times meters is kilogram meter squared per second squared. So we then have E equals mc squared. So energy in joules equals kilogram times meters per second. Square that quantity. We get joules being called the same thing as a kilogram meter squared per second squared. I think we got it. So E, in fact, equals mc squared. Let's move on from that. So to convert mass to its energy equivalent, you just multiply the mass in kilograms by the speed of light, meters per second squared. Let's try it. You can see these are not going to be challenging. other than the kind of the craziness of the units involved. So, question. How much energy is released when an electron meets an anti-electron, known as a positron, and is annihilated? That means turned completely into energy. Well, we're going to need to know the mass of the electron. Right here, mass of the electron, the rest mass of the electron, is 9.11 times 10 to the minus 31 kilograms. Mass of the electron. Lovely. We know the anti-electron is the same in every way, certainly the same mass, simply has the opposite charge. So what is the mass of both particles? From the reference table we got that. We know that the antimatter particle has exactly the same mass. All right, so the givens. What do we have for givens? Well, we have the mass of the electron. We have the mass of the positron, that's the anti-electron, that's E+, and they're the same. We have C is 3.00 times 10 to the 8th meters per second. The formula, E equals mc squared then, and we solve it. E equals mc squared, so you have 2 times 9.11 times 10 to the minus 31 kilograms, right? Because the mass of both of these particles is going to be annihilated. Good, so that's the mass that we're killing off, 2 times the mass of an electron. That's the speed of light. Don't forget to square it. When we do all that, we get 1.64 times 10 to the minus 13th joules. But what if they asked us to convert that to electron volts? Remember what we multiply by? We're just multiplying by 1. So 1.64 times 10 to the minus 13th joules, this form of 1 is going to be 1 electron volt, is the same thing as 1.6 times 10 to the minus 19th joules. The joules cancel, leaving us electron volts. We would end up with 1.02 times 10 to the 6th electron volts. That's a lot of energy there. But remember, an electron volt is an exquisitely tiny amount of energy. So let's think of this. How does a proton compare to the universal mass unit? So here's the universal mass unit. So we're going to be talking about this now. We're also going to be talking about the rest mass of the proton, and notice that it is the same, approximately, as the rest mass of the neutron, at least out to 3 significant figures. The rest mass of the neutron is a little bit more, but comes out the same in 3 significant figures. So let's take a look at this. Right? So the mass of the proton, 1.67 times 10 to the minus 27 kilograms. Speed of light, we got that. Formula, E equals mc squared. And we just multiply these. Don't forget to square that. We end up with 1.50 times 10 to the minus 10th joules. We're going to want to convert that to electron volts. We multiply by 1 again. Joules cancel. We're left with electron volts. We get 9.39 times 10 to the 8th electron volts. Let's convert that to mega electron volts. If you're ever unsure of what mega means, that's 10 to the 6th. Okay, so converting that, EVs on the bottom, mega electron volts on the top, so the EVs cancel. And 1 mega electron volt is the same as 1 times 10 to the 6th electron volts. So we end up with 9.39 times 10 to the 2 MeVs. That's, well, take a look at the universal mass unit. At this level, mass is often given as its energy equivalent. Universal mass unit is 9.31 times 10 to the 2 MeVs. Okay, so we see that a proton is slightly greater than the 9.31 times 10 to the 2 MeVs for the universal mass constant. You can ask the question, why is that so? One universal mass constant is 1/12 of the carbon-12 atom. So you take the mass of the carbon-12 atom and just divide it by 12. Okay? So where did the extra mass go? Right? A proton has a little bit more mass than what we have as 1/12 of the carbon-12 atom. Turns out the strong force binds the nuclei so hard, the strong force forces the nuclei to come together with such intensity, some of the mass is lost as energy. And interestingly enough, that is why stars shine. Stars are shining because the strong force is binding nuclei so hard together, hydrogen forming into helium, at least in the initial stages, that some of the mass is turned into energy. So the very fact that stars shine, E equals mc squared, ties everything together. You now have completed physics. You go, guys.